Before the universe came into existence, there was nothing. No stars, no planets, not even space or time. It was an absolute void beyond comprehension. In this nothingness, there were no physical laws, no matter, and no energy. It was not darkness, for there was no light to contrast it, no silence, for there was no sound to fill it. Physicists describe this as a state beyond space-time itself, a realm where the very framework of existence had not yet emerged. And yet, from this timeless void, everything, the galaxies, the stars, and the atoms that form us, would one day arise. Understanding this profound absence sets the stage for the story of how everything began. For centuries, philosophers imagined nothingness as a true void, complete non-existence. But modern physics paints a stranger picture. What we call empty space is actually alive with invisible activity. In quantum field theory, even a vacuum is filled with virtual particles that appear and disappear in less than 10 to the minus 23 seconds. These quantum fluctuations produce what is known as vacuum energy, estimated to be around 10 to the negative 9th joules per cubic meter in today's universe. This means the universe never experiences true emptiness. The nothing that preceded everything may have been a quantum foam, a field of potential waiting to erupt into existence. Quantum fluctuations are unpredictable, microscopic shifts in energy. In the vacuum of space, they can create particle-antiparticle pairs from seemingly nothing, in line with Heisenberg's uncertainty principle. Some cosmological models, like those proposed by physicists Alexander Vilenkin and Edward Tryon, suggest that a particularly large fluctuation could spawn a self-contained region of spacetime. If that region expanded faster than it collapsed, it could evolve into an entire universe, a process requiring only zero total net energy, because the positive energy of matter could be balanced by the negative energy of gravity. In this sense, the universe might literally have borrowed existence from nothing while still obeying the laws of physics. Roughly 13.8 billion years ago, our universe began with a sudden expansion of energy and space, the Big Bang. It was not an explosion in space, but an explosion of space itself. At 10 to the minus 43 seconds after the beginning, the Planck time, the universe was smaller than 10 to the minus 35 meters, and the temperature exceeded 10 to the 32 Kelvin. Gravity, electromagnetism, and the nuclear forces were still unified, forming a single superforce. This era, known as the Planck era, is beyond the reach of current physics. Even Einstein's relativity and quantum mechanics break down there. But what followed, we can begin to understand. Around 10 to the minus 36 seconds after the beginning, the universe underwent cosmic inflation, an unimaginably fast expansion. In less than 10 to the negative 32 seconds, it grew by a factor of at least 10 to the 50, from subatomic size to macroscopic scale. This inflation smoothed out the early irregularities, explaining why the universe appears flat and uniform today. Tiny quantum fluctuations during this period were stretched across cosmic scales, becoming the seeds of galaxies and clusters billions of years later. Observations from the Planck satellite 2018 confirm the imprint of these early fluctuations in the cosmic microwave background, CMB, the oldest light in the universe. As inflation ended, the universe entered a period called reheating, where its energy transformed into particles. Within the first 10 to the minus 6th seconds, quarks combined into protons and neutrons. At about 3 minutes after the Big Bang, the temperature dropped to around 10 to the power of 9 Kelvin, allowing these protons and neutrons to fuse into light elements, mainly hydrogen, approximately 75%, and helium, approximately 25%, with traces of lithium. This process, called Big Bang nucleosynthesis, defined the chemical foundation of everything that would come later, from stars to planets to life itself. By 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin. This allowed electrons to combine with nuclei to form neutral atoms, a phase known as recombination. For the first time, light could travel freely through space. That ancient light still fills the universe today as the cosmic microwave background, CMB, faint radiation with a temperature of 2.725 Kelvin, discovered in 1965 by Penzias and Wilson. The CMB gives us a direct image of the universe when it was less than 500,000 years old, the cosmic equivalent of an infant photograph. In the early universe, matter was spread almost evenly, but not perfectly. Tiny fluctuations in density, only 1 part in 100,000, were amplified by gravity over millions of years. Regions just slightly denser attracted more matter, growing into massive clumps. These eventually became galaxies, galaxy clusters, and the vast cosmic web of filaments and voids that define the universe's large-scale structure. Without these microscopic imperfections, the cosmos would have remained a featureless fog. No stars, no planets, no life. Around 200 million years after the Big Bang, gravity pulled together clouds of hydrogen and helium, igniting the first stars. These were the population 3 stars, immense, with masses between 30 and 300 times the mass of the Sun, and surface temperatures above 50,000 Kelvin. They lived fast and died young, burning for only a few million years before exploding as supernovae. In their deaths, they forged heavier elements, carbon, oxygen, silicon, iron, seeding the cosmos with the raw materials for planets and eventually, life. Over billions of years, this process repeated. Stars formed, lived, and died, enriching space with new elements. The gas and dust expelled by one generation became the building blocks of the next. Galaxies merged, supermassive black holes formed at their centers, and vast structures evolved under the slow dance of gravity. Today, the observable universe contains an estimated 2 trillion galaxies, each with 100 to 400 billion stars and likely trillions of planets. Every atom in your body was once inside a star. The cosmos recycles itself, eternally. Within these galaxies, new stars gave rise to planetary systems. Around 4.6 billion years ago, our own solar system was formed when a vast cloud of gas and dust came together under the influence of gravity. At its center, the sun ignited, and from the surrounding material, planets were placed in motion, including one uniquely suited to sustain life. On this world, the conditions were set for something extraordinary to begin. In time, life appeared, intricate, balanced, and purposeful, carrying within it a profound sense of design and order. From the dust of creation emerged awareness, as the universe became capable of reflection and wonder. Perhaps nothing was never truly nothing. Maybe it was potential, a field of infinite possibility, waiting for the right fluctuation to ignite existence. In this sense, the emergence of matter, life, and awareness were not accidents, but natural expressions of the laws written into the universe itself. Existence is not a miracle outside physics. It is the unfolding of what was always possible. Is our existence the result of chance, or the unfolding of a greater cosmic order? Across the vastness of space, matter was shaped and arranged according to precise and harmonious laws. Within this grand design, awareness emerged, not as an accident, but as a natural expression of the universe's depth and intention. When you gaze upon the night sky, you are witnessing the universe reflecting upon itself. Every thought, every discovery, every act of wonder is the cosmos recognizing its own beauty and meaning. From the emptiness of nothing to the boundless expanse of everything, the journey of existence continues. The cosmos evolves, complexity deepens, and awareness expands. Our quest to understand where we came from is not just science, it is the universe's way of remembering itself. The story of everything is still being written.